If you've been following the deep learning field for a while, you may have heard about human pose estimation. For those of you who aren't really familiar with it, human pose estimation is a field in deep learning where we try to understand a human's pose or their orientation. Traditionally, human pose estimation algorithms identify the key joints on a person's body and connect them to form almost like a skeleton. This concept of understanding a human's pose can be applied across various fields. For example, apples and emoji, where they attempt to identify the key points on a person's face and then turn that into like an emoji, like a horse or like I don't know, like cool emoji. Or another example is the basketball trainer app Homecourt, which can actually analyze your shooting form or your workout form and tell you how good it is or how to improve it, which is really cool. I've actually used that app in the past a lot. It's a cool app. So in the deep learning field, research and academia play a huge role in advancing the field. So in today's video, we're going to talk about a simple yet thorough architecture which allows us to effectively perform human pose estimation. So without further ado, I present to you Hourglass Networks. So human pose estimation is quite a complicated yet really interesting part of deep learning. So here's kind of how we'll tackle it in this video. First, we'll take a look at human pose at a really high level. So we'll look at what it is, we'll look at examples of it, and we'll look at problems right now that we have to tackle in the field. Then after that, we'll look at Hourglass Networks specifically at a high level again. So what are they, why are they so effective, and what makes them so much better than the other architectures that are available right now? And then we'll look at the layers which this Hourglass network is made of. And finally, we'll walk through the network step by step, so each layer in each section. Yeah. So firstly, we'll be looking at human pose estimation in general. So human pose estimation, like I mentioned before, is essentially just finding and connecting key joints on a human body to understand the human's pose or their orientation. And also this can be done in both two dimensions and three dimensions. So an example of each. So for three dimensions, we can look at apples and emoji. So if you see the GIF that I'm playing out of edited in by now, you can see how this technology can map the key points on a face, and it's able to actually overlay an emoji. Now this is done in 3D. Clearly, it's not done in 2D. But this is a really cool application of human pose estimation. Especially one that we all are familiar with. And another example of human pose estimation is Homecourt, like I mentioned before, a really cool basketball app that can actually analyze your like shooting form and your like workout form and stuff, and tell you if your form is bad, and it can like correct your form. It's almost like having a personal trainer at home, but it's your phone. So that's really cool. That's also a really cool application of human pose estimation. Now this is 2D human pose. They're not doing 3D because it's not really required in this sense. So yeah, so both 2D and 3D are useful. Don't think just because 2D is two dimensions, it's not useful. No. They're both have various applications, which are all really cool. But human pose estimation is not perfected like all parts of deep learning. Some of the key problems in this field are sometimes people have either very small or barely visible joints. That makes it hard for the algorithm to sometimes detect. Sometimes, like when you have baggy clothing, it's hard to identify where the joint is. Like maybe you can't exactly pinpoint where the shoulder is on some guy with like a huge shirt on. That'll be hard for the algorithm. Or maybe the lighting changes. Maybe there's like really poor lighting in a section of the image where you can't see a certain joint, so it'll be really hard to predict where it is in the image. So yeah, so there are architectures that are tackling that, and as we will find out later on, the Hourglass network will actually be able to tackle most of these problems due to its encoding decoding structure, which allows it to perform both top down and bottom up processing, which was a huge advancement compared to all the older architectures. But that is what we will be talking about in the next section. So like I just mentioned, when I will look into the different types of architectures, network architectures that are used to understand human poses. So Hourglass networks weren't the first architecture to tackle this problem. There have been many attempts before to do this, and very successful attempts also. One of the first attempts was an architecture called Open Pose, which is a CNN that which is a CNN that does feature extraction, and then it does object detection, and then after like 40 years and like a billion other CNNs, it outputs the predictions. So like not very efficient. Um, and there have been also many other attempts with architectures like Mascar CNNs, an architecture called Deep Cut, another architecture called Alpha Pose. Um, However, they're all not super efficient, but efficiency is not the biggest problem here. The biggest problem is that they each of those architectures I just mentioned, they either do top down or bottom up processing. So top down is essentially when we first localize where the person is in the image, so we like find the person in the image, and then only then we would assign the key points to a person. So first localize, then assign the key points. And then bottom up processing is where you would start off with detecting the key joints and then assign them to a person. And then obviously the final step for both top down and bottom up is to connect the key joints. But the parts that I mentioned before are the main differences. But what Hourglass networks allow us to do is they allow us to do both of them at the same time, which makes our predictions a lot more accurate because we have more information. So that was one of the biggest advancements that these Hourglass networks were able to do. So yeah. So Hourglass networks are a type of convolutional encoder decoder, which is able to perform human pose estimation really effectively. And they do this much effectively than the other architectures I just mentioned because they include both the spatial and the feature information of an input. This is due to it's both the encoding and the decoding stages of it. So the encoding stage, it deconstructs an input into a feature vector, and then the decoding stage combines the earlier layers of the encoding stage, which have a better spatial understanding, so they understand more where objects are in the image, and it combines it with the later layers in the encoding stage, which have a better feature understanding. So it understands more what the objects are in the image, and it combines all this information to overall just get a better understanding of the inputs themselves to create better predictions. So yeah, that's basically Hourglass networks. So at a high level, of course. So Hourglass networks, they before diving really deep into them, we should really understand the layers that they're made out up of. So first of all, they're made up of convolutional layers, pooling layers, residual layers, bottleneck layers, and upsampling layers. So first of all, convolutional layers, what they do is they're able to automatically learn features of an input. So before people had to tell a network what type of features to look for, but what convolutional layers can do is they automatically learn what are the best features that corresponds to an object in an image, which completely transformed the world of deep learning. Instead of having the people spending like thousands of hours trying to figure out what is the best way to classify a car, you can literally just like put it in put it in like a you create like a convolutional network and they'll just do everything itself. So completely revolutionized the deep learning field, and it's used in Hourglass networks to, like I just mentioned, to deconstruct the input and to really understand what the input is by understanding the specific features of the input. Uh, so and then after that we have the pooling layer. So what the pooling layer does is it takes the outputs from the convolutional layer, which are feature matrices, and it essentially only focuses on the most important features. So let's say you have an output, you have a feature matrix, and you have really high value pixels, which represent sections in the image that have the feature that we're looking for, and you have really low value pixels, which basically are saying that this section does not have the feature we're looking for. What this max pooling layer is going to do is it's going to scan over the image, and it's only going to select the sections that have the features we're looking for, and it's going to ignore all the other ones that don't have the feature we're looking for. So yeah, so it basically like ignores like most of the image, except for the important parts. So it makes it a lot more easier to do convolutions since the input is tremendously downscaled, and it also makes it a lot easier on the computer. It doesn't take up as much memory, which allows us to have much deeper networks. Next up, we have the residual layer. So the residual layer, first announced in the ResNet, solves the vanishing gradient problem. So the vanishing gradient problem that occurs when the gradient in backpropagation converges, so minimizes way too fast. Um, and when that happens, essentially our network, the weights stop getting updated, and then the network stops learning. So basically, we're just like wasting iterations. It's like useless. So how it does this is it takes earlier layers in the network and it pushes them deeper into the network, allowing the next activation be equal to this new layer's activation, meaning that the local gradient will only be one, since the derivative of itself, a derivative of a function of itself is just one. So this means that if the local gradient is one, and the incoming gradient, it won't get smaller, because just multiplying a number by one just stays the same. So this allows us, if we like do this like a couple times in our network, um, uh, it would it would make the gradient converge much slower than if we wouldn't do this. So yeah, it's a big part of Hourglass networks, since we not only use this in the network itself to allow the gradient to converge much slower, but we also use it to combine the spatial and feature information in the upsampling or the decoding stage, which is the foundation of this whole network. So residual layers play a huge part in this network. Um, and then we have the bottleneck layer. The bottleneck layer is it's uh, it's it's a variation of the residual layer. So residual layers, in our case in the Hourglass network, we use a lot of 3 by 3 convolutions. So what the bottleneck layer does is, instead of having two 3 by 3 convolutions, it replaces that with two 1 by 1 convolutions and one 3 by 3 convolution. So this makes it this actually makes it a lot more computationally efficient, allowing for much deeper networks, since we're not like wasting all of our computational power on like a couple layers. And yeah, so it allows for much deeper networks, which is always better. The deeper the network, the more features are extracted. Um, and then oh yeah, and this is used tremendously throughout the Hourglass network, as you'll see each one of the blocks in the Hourglass network there, that's a bottleneck layer. So used a lot in our Hourglass network. Very important concept to understand. Um, And if you feel like you don't understand it, I have a lot of resources linked in the description where you can read more and watch more about them. But anyways, the upsampling layer, the upsampling layer, um, this layer essentially takes images and it makes them bigger. um, it does this by using simple math, um, and it would essentially estimate the pixel values in between two normal pixels. So it would take like a small input, or it would take just an input, and it would estimate what pixels are in between these two pixels using math. um, and essentially in the Hourglass network, we would do this a repeated amount of times to take our image, to take our feature matrix and actually upscale it to an image, which is combined with the spatial information, of course. So yeah, we use upscaling layers a lot in our Hourglass network. And yeah, so now I think that's everything. Yeah. So just to review an Hourglass Networks, just looking at the diagram here, we can see two main things. There are two sections of the Hourglass Network. There is the encoding section and the decoding section. And each section has four cubes, where each cube represents a bottleneck layer. Um, and you can see that after each cube, we kind of preserve that cube, that spatial information, from the encoding layer and pass it to the decoding layer, and this is how we are able to combine the spatial and feature information. Um, so yeah, in the first, starting with the, so we'll dive deep into the each cube. So the first cube is actually a little different to the other cubes. We start off with the 7 by 7 convolution, add with the batch normalization and a Rayleigh activational function. Then after that, we pass the input into a bottleneck layer, and after that bottleneck layer, we split off. We split the input off, or the spatial information off into a residual layer, which we preserve for later. And then we do backspool and two bottlenecks. Um, and yes, yeah, and then after that, we we have this for the second, third, and fourth cubes on the encoding stage. We have, it is very simple. It's just a bottleneck and a max pool. And right before the max pool, we preserve the spatial information for the decoding stage. After that's repeated, after the fourth layer, we have three bottlenecks, which create the feature map of our network, and after this stage, we start combining, we start upscaling. So we start combining the spatial information with our feature maps to upscale the feature map. So as you can see, the plus just means element-wise addition. So we just multiply. I mean, we add all the elements in our in the layer containing the high spatial information with the layer containing the high feature information. And then after that, it's a simple, just we do for the all the layers in the second part, in the decoding stage of the network. We just have an upscaling layer, um, from the previous, from we upscaled the previous decoded layer, and we combine it with the spatial information, like I said before, to get a better understanding of the input. And then in the output, we do two convolutions, two 1 by 1 convolutions, and we make our heat maps, and then we pass the heat maps into a 1 by 1 convolution to make sure it's the same size as everything else, and then we perform element wise addition with the inputs, um, and with the inputs and both the network's outputs. So the network has two outputs because one is the heat maps, one is the heat maps, and the other one is the inputs that we're going to pass on to the next network. So you see how how we have incoming inputs from the beginning, from the start of the network, the inputs that we inputted into our Hourglass network. So yeah, that's basically what the inputs that we're passing on to the other network are. So so we have three input. We have three functions that we're performing element-wise addition with. The inputs from the inputs from that we inputted into the network, the heat map predictions, and the the inputs which we will pass to the end of the next Hourglass network. So yes, we are in for human pulse estimation. We're using multiple Hourglass networks stacked on top of each other. And this right here, and then we perform a loss after we do that element wise addition. And this right here is what we call intermediate supervision. So normally in a network, you perform the loss function after the whole training iteration is done. Now in this case, the whole training iteration will be done only after we've passed the input through all eight Hourglass networks. I think it's eight that we use. I'm not sure. But in this paper, the authors propose to calculate the loss after each Hourglass network. So this gives us a better understanding of the network's error, and how accurate each heat map prediction is. So it's definitely a huge factor of measuring the network's accuracy. So yeah, that's about it of Hourglass Networks. Um, yeah, I really hope you enjoyed that because it was really fun to make, and it's really cool architecture. Looks nice. I know looks isn't a great way to judge a deep learning architecture, but it looks really cool, and it's very useful. So yeah, I really hope you enjoyed that. Uh, yeah, and then the next video we'll actually be coding it. We'll be coding it from start to finish. So that'll be fun. We'll be coding it in TensorFlow. So yeah, definitely check back for that. And let's see.